Hey guys, Mr. Backerberg here. In this video we're going to look at analyzing graphs of rational functions. So we're going to take a look at an example in here, and we're going to look at the function f of x equals x minus 1 over x squared minus x minus 6. And we're going to look at finding a bunch of different things with this function. We're going to find the intercepts, so the x-intercepts and the y-intercepts. We're going to find any asymptotes that our graph might have, and we're going to look at using our limit notation to describe the behavior of our graph. Now, as we're looking at this function, since it's a fraction, I want to talk about the domain of the function. So the first thing I want to look at doing is actually factoring out the denominator. So with that, x squared minus x minus 6, if we think about sum and product factoring this, it would be x minus 3 and x plus 2. So if we're thinking about the domain of this function, we would want to think about the values that would not be safe to plug in for x, and we're trying to avoid 0 on the bottom of the fraction, so it would not be safe for us to plug in 3, and it also wouldn't be safe for us to plug in negative 2. Now, while we've got this function in its factored out form, we should look to see if there are any factors that will cancel out. But there aren't, because we've got the x minus 1 on top, and the two factors we've got on bottom are the x minus 3 and the x plus 2. So none of that's going to cancel out. Now, as we start talking about asymptotes, I want to look at the vertical asymptotes first. Now, we already know that we're going to have domain issues at 3 and at negative 2, and that's actually going to lead us into our vertical asymptotes, because when we find the vertical asymptotes, we set the denominator equal to 0. I'm going to look at the factored out version, and if we were to take each one of those factors and set them equal to 0, we would get an asymptote at x equals 3 and at x equals negative 2. Now, as we're looking at the end behavior of our graph, we want to look at the powers of x on top and on bottom, and because the power on top is smaller than the power on bottom, then we're going to have a horizontal asymptote along the line y equals 0. Now, when we're finding the x-intercepts, I want to look at the numerator of my fraction, so the x minus 1, and I'm going to set that equal to 0. And then solving that, we would just have to add the 1 over to the other side, so we have an x-intercept at x equals 1. And then for our y-intercept, I want to look at f of 0, meaning that I'm going to plug 0 into my function. And it doesn't matter which version of our function we plug this 0 into. I'm going to plug it into the factored out version, so I would get 0 minus 1 over 0 minus 3 times 0 plus 2. So on top, 0 minus 1 is negative 1, and on bottom, 0 minus 3 is negative 3, 0 plus 2 is 2, and if I take negative 3 times 2, I'm going to get negative 6 on the bottom. And these are both negative, so they're going to turn positive, so we're going to have a y-intercept at 1/6. Now let's get a set of axes in here so that we can do some graphing. First thing I'm looking at is that we have two vertical asymptotes, one of them at an x value of 3 and one of them at x equals negative 2. So I'm going to draw those in on my graph. I also know that we're going to have a horizontal asymptote along y equals 0. Now, as far as our x-intercept at x equals 1, if I find that x value of 1 on my graph and I plot that out, notice that our graph will actually cross through this horizontal asymptote in the middle, but that's okay. Horizontal asymptotes refer more to what's happening on the far ends of our graph, the left end and the right end of our graph. Now, we're also going to have a y-intercept at 1/6, so on our y-axis, just a little bit above 0. So we can kind of get an idea of what's happening in the middle of our graph. If I look at these intercepts and connect them and then use the asymptotes to help me up, this piece of the graph is going to have to follow this asymptote up, and as we work our way through that x-intercept, we're going to have to follow this other asymptote down. But we're not really sure yet what's happening on the left-hand side or on the right-hand side, whether we're on the top or the bottom of our asymptotes in there. So what I'm going to do is actually plug in a couple of x values. So we know that we've got a vertical asymptote at negative 2, but what I'm going to do is go a little bit left of negative 2 to figure out if we're going to be on the top portion or the bottom portion. So what I want to do is plug in an x value that's happening left of that negative 2. So let's say we wanted to plug in negative 3. I would plug negative 3 in for my x. On top, when we do that, we're going to get negative 4. And on bottom, we would get 6. So that would reduce down to negative 2/3. So if I plot that out, go left 3 and down 2/3, we would have this point right here. So that tells me that that portion of the graph is happening below this horizontal asymptote. So we follow this horizontal asymptote in, and then we'll have to follow this vertical asymptote down. Now if I do something similar on the right-hand side, I want to plug in a value that's right of 3. So maybe we'll plug in 4 there and see what happens. When we do that, on top plug in 4 and we should get 3. On bottom we'll end up getting 6. So that reduces down to 1/2. So over at 4, I'm up at 1/2, which tells me that this portion of our graph is happening on top. So our rough sketch of our graph would look something like this. Now I do want to use some limit notation to describe some of the behaviors of our graph. And the first thing I want to look at is the behavior as we are approaching our vertical asymptotes. So remember, we've got one vertical asymptote at negative 2. So I want to write out a limit as our x values approach negative 2 from the left-hand side, and I want to see what my function is doing. So starting on the left-hand side, as we get closer and closer to negative 2, our graph starts decreasing very rapidly. So we would say that this function is heading down to negative infinity. But if we look at the limit as x approaches negative 2 from the right-hand side, so starting on the right-hand side and getting closer and closer to negative 2, then this middle portion of my graph increases very rapidly. So we would say that our function is heading off towards positive infinity there. But we've got another vertical asymptote happening at 3, so we want to use some limits to describe the behavior there. So the limit of our function as our x values are approaching 3 from the left-hand side. So as we get closer and closer to 3, this middle chunk of our graph is heading down to negative infinity. And as we look at the limit of our function, as we approach 3 from the right-hand side, so on this right-hand side, as we get closer and closer to 3, our graph is heading up very rapidly. So we would say that the function is heading up towards positive infinity. So that takes care of the behavior around the vertical asymptotes, but now I also want to talk about the behavior with the horizontal asymptotes as well. So when we're looking at horizontal asymptotes, we want to look at what's happening on the far left-hand side of our graph and the far right-hand side of our graph. So to look at the far left-hand side of our graph, we're going to look at the limit of our function as our x values keep getting smaller and smaller, so heading left to negative infinity. And as we look, this portion of our graph is getting closer and closer to that asymptote, which is happening at 0. So we would say that our function is approaching 0. And then as we look at the limit as our graph is going out to the far right-hand side, so the limit of our function as x is approaching infinity, again, this chunk of our graph is getting closer and closer to that horizontal asymptote at 0. So we're going to say that our function is approaching 0 there. Now I want to look at an example in here where we've got an end behavior asymptote that's something other than a horizontal asymptote. So we're going to look at the function f of x equals x cubed minus 3x squared plus 3x plus 1 all over x minus 1. Now notice with our function, the power on top is bigger than the power on bottom, meaning that we're actually going to be able to do a little bit of division in here. Now because we are dividing by something that's linear, we can either do long division or synthetic division. Synthetic division is going to be a little bit quicker, so I'm going to do that in here. So we're going to have 1 and negative 3 and positive 3 and 1, and then we're going to be dividing by 1. So we drop down the 1, we multiply, and then we add to get negative 2, and then we multiply to get negative 2 again, add those up and we'll get 1, and then 1 times 1 is 1, so we'll add those together to get 2. Now if I take this and put my variables back in there, we started with a cubic function, we did one round of division, so we're going to have to drop the power by 1. So this 1 is on an x squared, this minus 2 is on a plane x, this 1 is our plane constant term, but then we have a remainder as well. And remember, remainders we take and we put over our initial divisor. So we can actually take this rational function that we were given to start with and rewrite it as x squared minus 2x plus 1 plus the 2 over x minus 1. Now we do still have a rational piece of our function on the back end with that 2 over x minus 1. So when we're talking about the domain of this function, we need to make sure that our x value is not 1, which is going to lead us to having a vertical asymptote at x equals 1. But if we're looking at our end behavior asymptote, what we're going to look at in here is actually this quadratic that we got in the front with this x squared minus 2x plus 1. If your numerator polynomial has a higher degree than your denominator polynomial and you do some division, then the quotient that you get when you do your division is actually going to dictate your end behavior asymptotes. So I want to look at this one graphically. So in my calculator, I've already got that original rational function typed in. I'm going to adjust the window just a little bit. I'm going to make my x min go down to -5 and my x max go up to 5, but I'm going to leave the y min and y max at -10 and +10. Now when I hit graph, we're going to get a picture that looks something like this. So we can see that our vertical asymptote is happening at x equals 1. But we can also see that as we're moving to the left and as we're moving to the right, our graph is displaying some different behavior than those typical rational functions that we've been looking at. They don't appear to be approaching a specific y value like we had with a horizontal asymptote. And that's because we've got a different type of asymptote happening because we were able to do that division in there. So what I'm actually going to do is go back to my y equals screen, and I'm going to type in that quotient that we got when we did the division. So that was x squared minus 2x plus 1. And now if I graph this out with my original function, then I can see as we're going further and further left, this blue piece of the graph is gradually approaching that parabola. And as we work our way out to the right-hand side, this other blue chunk of our graph is getting closer and closer to that parabola. So that x squared minus 2x plus 1 is actually our end behavior asymptote. As we work our way out to the left-hand side and to the right-hand side, our blue graph keeps getting closer and closer to that parabola. That's going to be it for this video. Thanks for watching.